That's the general picture. And so let's see, why do we care about probability? James Clerk Maxwell once said that if something is totally certain or totally doubtful, we do not need to do research about it. So the true logic of this word is the calculus of probability. So we always need to care about probability. I think that's the gist of AR for science. AR for science is about quantifying uncertainty. And we do have different sources of uncertainty in different disciplines of science. So everybody talking about AR for science, but I think we should have AR for chemistry, AR for biology, and AR for climate science. So AR for climate science differs from the AR for other disciplines because it has these three unique features. And since it has these three unique features and we have a categorization of different uncertainties, we need to write these uncertainties into some source of uncertainty. And Yang Le has mentioned that we need to care about probability because these four reasons. The first is that the world might be intrinsically stochastic, so we care about quantum mechanics, but at the scale we care about, it's a pure deterministic world. It's deterministic does not mean that it's predictable. And the other three reasons are that we cannot fully observe the world, which means that we never have a full, we never observe every detail to the very to a detailed accuracy that we need. And the second is that we do not fully model the world. So the model always makes simplifications. And the fourth one is that the world is chaotic. I think the last three reasons that drive the machine learning researchers to adopt a probabilistic perspective are the reasons that we need to care about in climate science. And in climate science, since we are dealing with a chaotic high-dimensional world that involves a lot of interactions among subsystems of different scales, and we can never observe the world to a full detail. We do not fully model the world. So those are the reasons we need to use probability to represent our understanding, to represent processes, to represent state, and to represent the different forcing, the response to different forcings. So why do we need probability in climate science? So first, we need to represent dependency among different variables. We always talk about there is a pattern here in this kind of circulation. There's a pattern there, but pattern means that there is if we want to quantify it, it's the probabilistic dependency upon different phenomena that can be quantified. And also we want to quantify the dependency between the unresolved variables to the resolved variables, so the so-called parameterization. And also we want to make use of incomplete data and missing information, such as inferring the climate state, which I will give an example in the later section. And we need to make probabilistic predictions because of two reasons. The first, we do not have a perfect initial guess. And second, we do not have a perfect model. So if we take into account of the initial state uncertainty and model uncertainty, we need to provide a spread of what is possible in the future, especially at an extended range like sub-seasonal to seasonal scale. And also we want to know how this kind of spread depends on the initial state, depends on how well we know the initial state, so-called opportunity or predictability. And lastly, we want to quantify likelihood. First, we always talk about climatology distribution, and we try to sample climatology distribution using long-term simulations and a stationary assumption. But when we cannot leverage this climatology information to help us guess the state of this huge system. And we cannot know how different model formulations influence the climatology unless we run many rounds of simulations. And we cannot know how different forcings influence the climatology, especially for those extremes. And we want to quantify the likelihood of different circulation patterns, different events to happen under different forcing scenarios as revealed by different models. So if we want to quantify these kind of things, we need to model probability. But how do we model probability? If it's a one-dimensional thing, it's super simple. We get a lot of samples here, and we can fit a curve to that. If the curve, it has some parameters, and we try to search a parameter so that the curve assigns the maximum likelihood to these samples. then this is a parametric fitting of PDF for these samples. And we can also use the bin box method or use kernel method. So for 1D situation, it's pretty simple. And for 2D situation, we can use something called copula, and it's still a parametric method trying to have something that link to one-dimensional distribution to a two-dimensional distribution, and then it will tell us what's the probability of a combined event of heat wave and drought. And then if we go to even higher dimension, what can we do? We cannot say that it follows some like Gaussian distribution, if it follows some gamma distribution. So those will underestimate the dependency upon different dimensions within this variable. And the most convenient way is to use generative model, which transform some easily sampleable Proud distribution and put the sample from this distribution into a black box, and it will have some transformed samples which will reveal the distribution we try to approximate. And this is kind of the most flexible and powerful approximation of some high-dimensional distributions. So we do have two words. There is timeline in our human civilization. So the born of Jesus Christ, like 2024 years ago, marked BC and AD. But now people see that maybe we're having some transform in our civilization now. So BC might be before ChatGPT, and AD is after diffusion. So we do have these two different models, and they mark the arrival of the new generation of generative models. And they give us some interesting things. And everybody here might be familiar with supervised learning, if it's a classification task, regression task, or even for AlphaFold, it's a regression task. We can guess which pixel belongs to which category by training a large neural network. So the neural network assigns the average maximum likelihood to the category that the training data's pixels belong to. Or we can use a 2D photograph to regress to the 3D structure of your face, and it'll give you this. And we can have the AlphaFold, we can have NERF, which if you see something from different angles and you try to interpolate between these angles and viewpoints, you will get a 3D modeling of this object. So supervised learning is pretty easy. It's just trying to extract some information from paired data samples. But this will not tell us a lot more, except that, for example, you can have some high fidelity data, and you get, for example, from low resolution to high resolution, and you can do supervised learning to know that, yeah, the low resolution contains some information about the high resolution thing. Or you can see that, or you can use some rainfall runoff model, and it will give you better runoff simulation because the data has more information than what you have extracted from some process-based model, but it will not tell you a lot more. It's just a benchmarking there. It tells you that you can do it, you still need to interpret it, but what else it can tell? It cannot inform us how can we develop better climate models. It cannot tell us what the climatology would differ if we get different model, if we get different forcing scenarios. But there's something called generative modeling, which trying to model the detailed dependency among different dimensions and of a whole dimension as revealed by different samples. And these are some representative examples of generative modeling. The first is called disentanglement. And if we have a selfie here, we try to transfer it into different styles, like Cezanne, Van Gogh, Monet, even Zebra. We can do it using a Sarkogan model. And at the very beginning, while I was familiar with supervised learning, I don't know how this was done, because I cannot imagine that Cezanne, Van Gogh, they draw a lot of selfies of me, and then I can put a new picture there, they will transfer it to their style. But actually, their drawings are forming a kind of distribution, and a photograph taken by a phone, it might be forming another distribution. If we can map each sample from this distribution to each sample in this distribution, we are doing something called domain matching, and we can resolve this problem of domain shift, which means that those two sample sets, they come from different distributions. And this is actually what we are doing in climate projection or in historical climate simulation. We're starting from 150 years ago and we try to run the model for so many years. We know that the two trajectory between model simulation and observation, they will never match. But the goal is never to match these trajectories. It's just to reproduce historical climatology. And we know that a requirement for climate models, for good climate models, is to reproduce the climatology. But we never say that it's also sufficient. It's also sufficient condition, which means that if a model can match the climatology of historical, of observed climate records, this makes it a perfect model. So it's necessary, it's also sufficient to make to do domain if we can do domain adaptation for climate models to match historical climate climate observations. So this has been demonstrated in Philip's paper and in my paper as well. And the other thing is about representation. So maybe 3 years ago, we are trying to write an email using Gmail. It's starting to, those words starting to flow out. It amazed me at the very beginning, but now we have ChatGPT, it's no longer a miracle. And we can, and at the same time, we are able to generate images from text. I think this is something interesting because we know that for some text, they correspond to different images. So how can we generate all those images that all correspond to the text they provided, and how can we edit these images? And we do not think, I was not thinking that this can revolutionize the whole field of generative modeling, but later, I think using a case example of precipitation estimation, I will demonstrate why this can be a revolutionary algorithm. So these are the examples of the generative modeling are extracted in a single day on Twitter when I was still lying in bed. I think they have shown some very promising directions in using generative models to accomplish something that we think are impossible. Like if you project this kind of north into 3 directions, you want them to show different figures here, and you can do super resolution like the top right, and you can make a figure consistent across different viewpoints. And I think they have some applications in the field of climate science, which I will talk about now. So let's say what we are doing in AR for climate science. Basically, we are doing 3 things. The very first is about inverse modeling. And we know that in climate models, there are some processes that has not been resolved. And we have some parameterization process that represent this unresolved process. And they have some free parameters that need to be tuned. So the model, when they are run, when we run it for a long time or we use them for weather forecast, they can match reality either by the trajectory or in some statistical sense. And this is forward model. And we need to find the correct parameters that give us the correct answer, which takes around 10 to the maybe 10,000, 100,000 rounds of these simulations. And we can do this kind of calibrate, emulate, and sample. That is, we just randomly sample some parameters and we create a response surface. That is how different parameters would give us different results. And we reverse this using some machine learning surrogator. So we get we get some good guess of these parameters. It accelerates the process of inverse modeling. And the second thing is about parameterization. That is, we not only care about we are not satisfied anymore because if we only tune the parameter, there are still some structural error in these climate models. And we want to say that you can learn from some high fidelity data, like high resolution simulations or even observations to represent those unresolved processes. And the right shows some large eddy simulation, and we can use a neural network to simulate this process and put it back to the dipole, couple it with the dipole, and model the turbulence transport of U prime, W prime. And the last is about acceleration. I think Lei has talked about this last time. It's about using, last year we have seen a lot of data-driven models. They can match or surpass state-of-the-art numerical models in predicting the weather up to 14 days. And they do have some drawbacks. the very first thing, and I think the very immediate drawback that I can find is their loss function. So they're trying to minimize the mean square error between models prediction and observation from reanalysis. But this observation and simulation, they are averaging for different input, for different variables, and for different places, although they assign some weights to these to different places, different variables, or different inputs. But still, it's just predicting the average of a lot possibilities. And there is nothing wrong with this if we just want to predict for a single step. But they are trying to roll it for many time steps into the far future. And if they run it for one time step and they are averaging over all possibilities and run it for another time, then there is a domain shift problem at the second step, at the third step. So making their predictions very blurry after rolling it for many times. And also this blurry results cannot support the diagnosis of, for example, precipitation or some downscaling. If you force a dynamical model using some rolled out predictions from these numerical models, you will see that they cannot give you the correct climatology. And should we stop there? And what can we do to solve them? I think if you take into account that we have problems in representing the process, we have problems in knowing which exact state we should predict. And if you combine these different kinds of uncertainties, if you go to generative modeling, I think you can resolve this problem. Gencast already have started to explore this direction, but I think there is one missing piece there. That is, there is some misunderstanding between the generative modeling community, and the ensemble forecasting community. And I try to resolve this in the first application here. But before that, this is the very end slide for the long introduction part. So how can we use machine learning or use generative modeling, use machine learning to improve climate science? I think we are going towards two different directions. So we can resolve geophysical fluid dynamics to 3 kilometers up to 100 kilometers here. But for the small scale processes, we cannot resolve it. And we do have partial high resolution simulations. We do have some targeted observations. And we try to learn from this referential data to improve the representation of these small scale processes. So this goes to the left. And for the large scale process, like seasonal forecast, like climate change, if we want to understand those with process-based models, we have to have different models, run them for a long time, which is the CMIP experiments. But still, we are not covering all the model configurations. We are not covering all the forcing scenarios. And we need machine learning to fill in the holes and to tell us what different models would agree and disagree about different processes. So these are the larger scales. And nowadays, all these applications are extending from this resolved scale to the small scale and to the larger scale. And I will talk about both sides in the rest of this talk. So the very first part is about numerical estimation. It's just an example. And I'm trying to use this to highlight a fact that is, on one hand, the generative modeling community should learn from the experiences of people who do ensemble forecast, who have been doing ensemble forecast for a long time. It tell us the deficiency of existing generative models. They are not perfect. They are not perfect for forecasting. So they should learn from generative modeling, from ensemble forecasting. And on the other hand, ensemble forecasting or some climate problems, they may pose a more crucial challenge to generative models. So currently, we do see a lot of improvements in generative modeling, but they have some benchmarks there. But I think the most crucial challenge is about making predictions of a high-dimensional chaotic system, for example, to make climate predictions. And then this can set up a new benchmark to evaluate different climate models, to evaluate different generative models. And here I'm using this question to develop using this task to develop a criteria of how to evaluate generative models. And based on this criteria, I try to highlight why diffusion model should be our choice to do prediction tasks. So we care about precipitation. And why would it rain? Why would we have precipitation? So we have the dynamical reason. That is, we have a convection at different scales, like convection scale, meso scale, and synoptic scale. And we do have microphysics telling us the interaction of different hydrogen materials. They collide and they fall and evaporate, and finally, at the very end, we get precipitation down on the ground. And in numerical models, how do we represent these processes? So for the dynamics, we try to use numerical solvers of the primitive equations to represent the movement, the large scale movement of the air and also its thermodynamical condition. And with that, we try to use some microphysical process representations. If you look at here, you know that it's highly empirical and a lot of parameters, a lot of equations here are wrong. They must be wrong. That's why we do not have a good numerical precipitation estimation. And we have to resort to machine learning to help us resolve this question. So we know that numerical models, they do provide very good wind predictions, temperature predictions, but their precipitation prediction is pretty poor. We know that we have some conceptual model. Like if we have certain circulation pattern here, we would have precipitation on the ground. And we can use a convolutional neural network to link the resolved dynamics to the observed precipitation. And we can have some inductive bias, like to represent the translational equivariant of this circulation pattern in relating them to precipitation. And we have the state variable as represented in a long short-term memory recurrent neural network. And we link them to precipitation observation here. We can get really good result. And even for some prediction task, we use resolved CFS circulation field to drive the statistical model that link circulation to precipitation, and we get really good result here. But we know that it's not enough because we can only resolve the circulation to a limited resolution. Here it's like half a degree, but precipitation takes place at like millimeter to centimeter scale, which is not resolved. And we know that given some circulation pattern, we cannot have a deterministic precipitation result. And if we want to know some extreme condition given this circulation pattern, we must know all the possibilities and derive our actions based on these predictions. So we want to estimate a probability of y given x using a lot of xy pair data. I know that you might argue that this is still supervised learning. Yes, here is still supervised learning. We're just giving all possibilities instead of just a single deterministic guess. But we'll come back to generative model in the later section. And we know that this is a very daunting task because under different forcing scenarios and different circulation patterns, we might have different precipitation, which they might have some structure. But for each circulation pattern, we only have one realization of observations, and we resort to diffusion models. So what is a diffusion model? Diffusion model try to develop a bijective mapping between some target distribution as revealed by some samples and some prior distribution, which we can easily sample using a stochastic differential equation. It's not done in a one-shot manner like previous neural network models like GANs or generative adversarial networks or like variational autoencoders, because it's a very complicated task and we do not want to do it in one shot. If we are doing it in a one step, and maybe we do not have a lot supervision signal there. So this is a very general formulation. We have this predefined Gaussian process that drift this target distribution to to a standard normal distribution. And for each of this equation here, we do have a reverse model that give that if we go from the prior distribution of a standard normal, we can go back. And the only thing we need to optimize is to have the mu and sigma here ready. And this mu and sigma are optimized by maximizing the overall likelihood of all this data. And we can derive it easily, not so easily, but if you follow this direction, you will get it. And once you get mu and sigma, you can have a random seed here, get the prior distribution sample and go back and you sample it again and again. You will have a distribution that trying to match the original target distribution. And what if you want to do some forecast? You need to have some conditioning information here. So there are two ways for now. For now, we do have two ways. The first is that you add some conditioning information into the training and inference process, which currently will give you some good result, like here. When we are drifting this, when we are training the model, we include some circulation information, the X here, and then the result will be influenced by two parts. The first part is the conditioning information, and the other part is the random seed, which after going through all this learned neural network, it will give us an estimate of what is possible. But because we do not explicitly determine what information comes from the conditioning information, what information comes from the random seed, it generally have a larger spread compared to what we want. So it always, in most of the conditions, it will cover what is possible, but it will not cover it very tightly. And this is pretty bad if we are trying to use it for predictions. And in the generative modeling community, they developed something called classifier-free guidance, which if you strictly follow their derivation, is the only way how we can enforce the information constraint from the conditioning information that is raised by a power. And then you will get the last part. And you can measure the ensemble forecasting capability of this model in a validation set to determine the value of this parameter omega. Trying to the importance of omega is to raise the significance of the conditioning information, so you can control how tight your forecast spread is in making your predictions. So this is the first method to add conditioning information to your generative model. That is to include the conditioning information in your training and in your prediction. And this is still supervised learning, right? It just gives you some possible outputs given some input, still supervised learning. And the other way is that you just train a generative model, unconditional generative model, and then you inject your constraint in your generation process. I think that one is more general because to train a model takes a lot of time. And if you just train it using some conditioning information, and if you change to a different conditioning information, you cannot use that model anymore. And also, if you, for example, here you are using it for CFS, and if you try to shift to ECMWF, you try to shift to CMIP models, you cannot use it anymore. And also, you only have very limited observational data, like paired data, to make the training possible. And if you can train an unconditional model and generate it based on some like only add constraints in your inference process, you can possibly answer different questions like if you change the model configuration, if you change to different resolutions, you can still use that model. I think that's very promising. And Philip and Mishi, they inspired me to explore more toward that direction instead of just doing some conditional modeling, which I appreciate very much. But still here is just supervised learning. And here are some results. I was pretty excited about these results 1 year ago. Still, this paper has not been out. It get rejected multiple times. I think There are some reasons there. Let me explain why. So we are modeling the precipitation around the circling around the typhoon eye of Typhoon Likima for 9 consecutive days. And the second line is our model using diffusion model that relates the circulation pattern to precipitation and generate a random sample for this specific circulation pattern. We get this. The third line is conditional GAN. You might argue that GAN is trained to discriminate whether a generated sample is true or fake compared to reality. Why the results here are not so realistic? Well, the reason is that we are training it in a conditional manner. And in our data set, we only have very limited typhoon case. So you cannot, there are a lot of statistical error here, which means that the data is not enough and your machine, your learning machine is not trained well. And the fourth one is conditional variational autoencoder. So it's like a single step, a one-shot diffusion model. And we know that it cannot give you really good results. And the fifth line is UNet. I think it's pretty popular right now. It's trying to relate circulation to precipitation. The CF is CFS reanalysis, which is pretty poor. And the last one is WOLF. We are using a 3-kilometer dynamical solver to resolve this process. But as you see here, we do not, some people believe that WOLF simulation is more realistic than observation, but we don't know. We are just learning from observation, and looks like the DRP model, diffusion-based precipitation estimator, is better matching reality. And this differs from our conventional wisdom in modeling precipitation. So usually in our existing parameterization scheme, what we did is that we only care about a single column. So if you can only care about a single column, you will get this kind of WOLF results. And the connectivity between different grid points is due to the connectivity of the circulation pattern in different columns. And they never take into consideration of their neighboring field, so it will never be scale aware. And second, they are, so the dynamical model, they are still deterministic results. They never inject, they seldom inject noise into their subgrid process. And if you want your parameterization scheme to be scale aware and uncertainty aware, maybe you need to adopt a different perspective, that is, give it a viewpoint of a larger scale, like a synoptic scale covering the whole typhoon circulation pattern, and then give you the results of the underlying precipitation. And also, this is the most important contribution of this work. We try to bridge the disconnection between generative modeling and ensemble forecast. So in ensemble forecast, we're kind of doing some conditional generative modeling, condition on the initial guess of your state, and give a spread, give some samples of what is possible. And this spread should fulfill two requirements. The very first requirement is that this spread should cover what is realized. It should cover what is realized, and the realization, the reality should never escape from the spread. And the second requirement is that conditioned on the fact that this spread has covered what is realized, the spread should be as small as possible. It should not be too wide, but it should still cover it. And this is not tested in current generative models. We test generative models using some conditional generative modeling tasks, but we cannot measure the coverage and measure the sharpness of our forecasting spread. And here we are testing how diffusion model differ from conditional GAN or conditional VAE using these so-called reality, efficiency, adaptability, diversity, sharpness criteria. And the most important thing is about the trade-off between diversity and sharpness. It should cover it and cover it tightly. So for this case, we generate 16 different ensembles. We get the ensemble mean and we get the ensemble variance. So that's what we report. We in ensemble forecast, we report the mean, we report the variance. And then we also get the mean absolute error, which is the difference between our ensemble mean and observation. So we get this mean absolute error. And what we want is that the ensemble spread is well correlated with the model's error, with the ensemble absolute error. Why would we expect that? If our ensemble spread is well correlated with the error, it means that before verifying the model has already told us where it is confident about its prediction, where it's not so confident. So if it's not so confident, we can have some detailed observations there. And we may say that if you are not so confident, let's be like kind of conservative about our predictions. So that's a very important thing about ensemble forecast, so-called skill spread correlation. And we see that GAN and VE, they do have poor skill spread correlation because they are not well modeling what is possible and they are not constraining what is possible using some techniques. And last, we want to see how the ensemble has covered what is possible. So we get the mean and max of this ensemble spread, and then we find if the observation falls within the mean max interval. And we see that this diffusion model offers the best guess of what is possible there. To conclude, I would suggest that if we want to push an ensemble forecast forward, we need to learn something from the generative modeling community. And the generative model, on the other hand, generative model, they have come to a bottleneck. That is, we have seen so many different generative models coming out every hour nowadays. And many of them suggest that they are surpassing the state of the art. But if we try to figure out if we try to examine it in some like chaotic system or in some real world climate system, then I think the advantage and disadvantage will be better revealed here. There's a very important paper from William Gilpin from UT Austin, and he's suggesting that there is a deep connection between generative modeling and nonlinear chaotic systems. So if we think deeper here, we are using generative models, and these generative models, they are essentially deterministic because they start from some pseudo-random number generator. And those pseudo-random generators are created by some chaotic system that is hard written in our computers. And then we come back to model this chaotic system using a transformed version of this pseudo-random number generator and forming a loop here. And I think there is a deeper connection, and these two communities, they can support each other. And a very immediate benefit is that generative model, they may come to a better test field if they are applied for like ensemble forecast. And then we should use our existing knowledge about what is a good ensemble forecast to help develop better generative models. I think that's the takeaway for this part. This is a very vanilla application. And in the very beginning, I was proud of this work, but now I think it's pretty trivial because we have found something more interesting. So let's come to a more interesting part, which is done by my student, Chao Jie. And we are about to submit this week. So this has a better flavor of generative modeling. It's about inferring climate state using incomplete information. And we are always trying to infer the state of the climate because it's chaotic and it's high dimensional. We cannot observe every part all at once. And once we observe it and we go forward in time, the uncertainty will grow and we need to observe it again. And we currently do have two different information sources. Or I would say it's one, but we're usually taking it as two. We use information. The first source of information is the observation from the current time step. We use the current time step observation to constrain our estimate of current step climate status. And the second source is the prediction from previous time step. But those predictions, they are just carrying information from previous time steps. So we have observation, we have forecast, helping us constrain the state of the climate system. Sometimes we call this technique as data assimilation. And those are the only two information sources. And here we're trying to see that there is a third source. And the third source is the inherent structure of this climate system as formulated by the underlying geophysical laws and the quasi-static boundaries of this whole system. So this is the situation we are facing. We only have limited observations. Guess what is the whole status of this system? And there are some pioneer work. They say that we can formulate this as a learning problem. That is, we only have partial observations and we want to reconstruct the whole field. So we can say that we have we can have some convolutional neural network. And for those regions where we have observations, we have the kernel node that there is a solid observation there. And for regions we do not have observations, we have the kernel node that there is no observation there, so you do not need to extract any information from that part. And the result is always the whole picture. But there are some limitations here. The very first is that they are formulating it as a regression task, which means that they assume there is a unique solution to each of these partial convolutions, which is never true. And this will not give us the information about uncertainties. And if they could give us information about uncertainties, we would know the value brought forward by each observational site. And even more, we could know where to make the next observation that is most informative. So we are trying to use some technique called imprinting or probabilistic imprinting. How it was done? We train a diffusion model, a probabilistic model that turns a random noise, a Gaussian noise, into a target distribution. And if we'll learn this prior distribution, and during the generation process, if we can blend in the observations, they can be anywhere, but if you can successfully blend in these observations, we can get some results that agree with the observed part and also provide the uncertainty about the unobserved part. And hopefully, this uncertainty would be a good uncertainty quantification of what is possible. And the very best part is that we can verify this using some observations and using reanalysis that were not revealed to the trained model. So that's the ideology here. And what we did here is that we started maybe 1 year ago, and we chose a very simple case example that is to estimate the hourly 2-meter temperature using ERE5 reanalysis data. And here is our methodology. We take 40 years of hourly temperature field data, and we noisify it using this predefined forward process. And then we learn the reverse model, learn the mu and sigma by maximizing the likelihood of this model assigned to the observations. So this is the generative part. And we try to generate the climatology of 2-meter temperature for this whole field. So if we have this very strong prow, and we do have some observational likelihood estimation, and if we have some method to imprint them into the generation process, hopefully we will get good estimates and good uncertainty quantification here. So here is a result on climatology, how we can reproduce climatology. we selected 1,000 ERA5 data samples randomly picked in the test set, and we generate a mean. We compute the mean, variance, skewness, and all kurtosis, minimum, maximum, all these statistics, and we will train a diffusion model using this ERA5 data, and we generate same number of samples here, and we compute the mean, variance, skewness, kurtosis, minimum, maximum. We cannot compare two high-dimensional distributions directly, but we can compare their statistics. And it seems that they are matching pretty good. And we can even use climate simulation data to create this kind of diffusion model. And that is, you get all these simulation data you take them as ground truth, and you train a generative model, and you generate all those samples and try to match the climatology here. So good, all good here. We get the climatology, and we see that the clean ERA5, which is called climate imprinting, our methodology, they can even discriminate between their training data. For example, if you look at Philippines, Ireland, and you see that FGOS is having a really high temperature on the island, while ERA5 is having a lower temperature, and those trend models clearly revealed these kind of differences. And we can also look at the spatial patterns. We look at the leading linear structure patterns like the UF, the first, second, third. They take almost same amount of variability. They explain same amount of variability, and the spatial pattern are pretty similar. And we can also look at the radial average power spectrum as a function of the wave number, still matching. So it means that now we can use diffusion models to reproduce the climatology. And the next step is to inject the observations into the generation process. And we use a method called repainting. That is, for a selected time windows, we replace the path where we have observations in the reversing process, and then we go back in time and we go forward, go back in time, go forward by multiple times to blend the observed part and unobserved part. So through this process, we have observations there, and their influence will be extended to places we have not observed. And here are the results. So we selected 4 days, and we keep some observation points that away from this impending process, and we test it in a later figure. These are 4 days from ERA5, and these are 4 days from the clean model. So we inject this observation and create a 100 ensemble of possible spatial field, and the correlation between the whole field, the observed field, and the guessed field is above 0.99. And we can also compute the spread, the ensemble spread. So you create an ensemble, and you have the spread, and then you compute the mean error of these ensembles, and you see that the ensemble spread and ensemble error, they are still well correlated, which means that the model already know where it is certain about the spatial pattern and where it is uncertain about the spatial pattern. So it is giving good ensemble guess. And we can have a 1 year round simulation, and we compute the mean error for models trained with different data sets and implanted with different data sets to reveal the error source from various factors. The very first factor is that you might train it using ERA5 data, but implanting using observational data, so causing some domain shift. And you might train it using some like simulation data and trying to implant using reanalysis or observational data. So another source of data of domain shift. And but for models trained with ERA5 or with FGOS, the climate simulation, they always show very similar patterns, although the model trained with simulation is showing a relatively worse performance. And we also examine how if a site is how far for the bottom left, the subfigure D, the x-axis is how far a point is away from its nearest station, and the y-axis is the average, is the distribution of RMSE for these points. So it's following a very like this kind of pattern showing that if it's close to observations, it has low estimation error. If it's far away from observations, then it has a higher error. And at the very end, we're trying to finish the last goal, that is to determine the value of each observation in determining the whole field state and trying to find an optimal way of the next most important observation in reducing the spatial uncertainty. We select different regions as delineated here, and we add an observation as a location that has highest RMSE, and then we recompute the RMSE for a whole year, and we get these results. We also remove an existing point here and see how it will increase the overall RMSE here. And in this way, we can quantify the value provided by an observational point. And hopefully in the future, we can make it like trying to add some reinforcement learning things and to go through the whole field to find where we should observe and to provide guidance for some optimal observation design, especially for like hurricane or for typhoon cases. So the last part is about probabilistic seasonal forecast. And we do see a rise, fall, and re-rise of empirical seasonal forecast. The first rise starts from like 100 years ago because we first started to observe the whole world, and we know that like there are some patterns like worker circulation, like El Nino, and we gradually embed this kind of statistical understanding into dynamical models. So the dynamical models, they can reproduce the statistical patterns that was found 100 years ago. But there are some problems there. That is, first, dynamical models, they cannot well represent how the interaction between the prediction sources and the predictant. And also, they have some problems with their initialization. And the very last reason is that they do not have a very big ensemble. We cannot afford like 1,000 ensemble for each model to run for 10 months every day to reveal what is possible in the future. So we do see a renaissance, that is, we can use data-driven model to make a surrogate forecasting. Like say, if we have ocean circulation like this, what would the precipitation or temperature anomaly be like in the future using some generative modeling formulation. And here is what we are doing. We collected 10,000 years of climate simulation. And we know that the uncertainty comes from model formulation, from the fact that we do not explore all the possibilities. So we try to predict what is possible in the future, given some initial condition and given some model. And we represent this using a conditional variational autoencoder, where the model is represented using some entity embedding technique. And from nowadays, it's pretty trivial. That is to represent in a dense vector and show the differences to different XY pairs, and then it will reveal the formulation difference of different models. And let's pass this part, and those are the data we applied. And here are the results. So if you look at sub-figure C here, this is how well the CAN-CM model is making dynamical prediction of precipitation. And for the sub-figure B, we learned how this model is representing the dependency between sea surface temperature and precipitation using model simulation. And then we apply it to reality, and we see how this is corresponding to a dynamical forecast. Interestingly, that even when we are learning from this model, in some regions, we are making better predictions than this model. And we would wonder why. And we show that the reason is because here we are using large ensembles. So we decrease the number of, and we have the NMME forecast from CAN-CM, which is a dynamical forecast, which has 8 ensemble members. And we increase the ensemble member from 1 to 8, and we see a consistent increasing of its prediction skill. But we cannot keep increasing it because it's pretty costly and they do not provide this dynamical forecast. But for this CVAE model, which is a generative model, it learns the probabilistic dependency from 10,000 years of simulation. And then we can keep generating novel samples here. It better explores what is possible. And by averaging all these ensemble members, we get better ensemble mean, and we see an increasing of prediction skill, and this prediction engine increase saturates if we have around like 300 ensemble members. So it means that we can learn from simulations to extract this relationship, and we can keep exploiting this space and making better predictions. And here we are showing how different models differ in their model embedding space in revealing different patterns. And if the model, the big M is where reality lies, and those characters are showing are labeling different models, and we see how they differ in their functional space. That is how they represent the dependency between SST and precipitation or temperature in the next season. And here is some like using some Selenium map to reveal the worker circulation, how different systems temperature influence the precipitation pattern here or there. And we can also, we explore something like predictability limit that is for different conditions, how the ensemble spread depends on different initial conditions, especially for ENSO. And we revealed that if it's La Nina case, it's a good opportunity of predictability for Pakistan. And this is shown in a recent paper, but during our first submission of this paper, it got rejected and nobody understands what we are doing. And we're currently having Qitong updating this work using diffusion models because we think CVAE has some severe limitations in capturing the whole distribution and in like limiting their in controlling their spread and sharpness and diversity. And hopefully we can better surpass current numerical weather prediction, numerical seasonal prediction models. So basically I will end here, and I think I have talked a lot about things that I have done or my team have done in the past 3 or 4 years, and basically I don't like them as much as I do like years ago because we think things are changing so fast, and we need a paradigm shift, and I really hope to come back again and tell about the new achievements. Yeah, Philip. Yeah, that's it.
Great. Thank you so much, Baoxiang. That was very interesting. And I'm sure that there's plenty of questions. So please feel free to either put them in the chat or directly ask them. I don't think there's a need to raise your hand or so. So just unmute yourself and feel free to ask.
Maybe I would start with a question concerning the in-painting you showed.
Mm-hmm.
Would you agree that the in-painting in this setup is kind of similar to a mask autoencoder? And like instead of doing a one-shot prediction where you mask an area and predict it like in one shot, in traditional sense of a mask autoencoder, you do noising iteratively. Yeah, would you think there's a parallel?
I think so. I read the paper masked autoencoder in 2021 when it became really hot topic. And the reason for using masked autoencoder is to learn a better representation of images. And they show that images are pretty redundant in their information. and they are not used for in-painting tasks, because if you look at their results, they give some really blurry outputs, right? And in the very different thing about our field and CV is that in computer vision, they care about semantics, they care about the whole picture, they care about the unity. But in our field, we are dealing with fluid dynamics. We care about details, and we know detailed error would grow to reach some large scale, to diverge the large scale trajectories. And I think this has some similarity. Actually, at the very beginning, I was trying to have Jie doing masked autoencoder, but once I've seen this, especially this figure. That's the thing that I really care about. It is you make an estimation of what is possible given some constraints. So what? It has nothing to do with what the community care about, unless this can be used for data simulation. It can be used for, like, say, if you only have this layout of observations, and we want to know the whole status of this field, and we also want to know where we don't know. We want to predict where we don't know. So you should have a good quantification of uncertainty here. And we have this figure, and also we do have some ground truth, and we can have this error map. And if these two are well correlated, it means that we are making good use of these observations to have low uncertainty here, but still we have high uncertainty here. And we should sufficiently sample these uncertain regions so that our predictions, they are not biased toward one direction. If you use masked autoencoder, you have something really flat in here, like the average of all possibilities. And you cannot use it to start a forecast, because in reality, we don't care about what is the average condition in the current. We care about what is average condition in long term. We care about what is possible in a long term. And that's the reason why we consider different models for the in-painting task. We are always dealing with the task of, like, guessing and making use of insufficient information, and making use of incorrect models in predicting where we are living. And I do think there is an opportunity for combining masked autoencoder with diffusion models. There's something called masked diffusion transformer. That is, in diffusion models, you are always trying to mask, let's say here, you're always trying to add noise to the whole picture and predicting the whole picture. But you can also mask out part of this image and use this noisified partial patches to predict the whole picture, or predict what is masked out. Actually, this increases the semantic integrity of these problems. And if you are doing, like, not only for atmosphere, but also combine it with ocean, and you must turn to transformers, because you no longer have a whole field there, and you want to maintain that the dimensionality, the variables here, they agree with the variables in the bottom, or in a very long distance. If you are doing monthly forecasting, you might need to take that into consideration.
Yeah, so you would basically have the concept of a mask autoencoder, but instead of applying a mask and then do one-shot prediction, where you get blurry outputs, you do it iteratively like the diffusion model. And this is basically then what you get from the diffusion part. Yeah.
Yeah.
Okay.
And it's doing it iteratively in a principled way, because these constraints here.
Great.
Thank you.
Thanks a lot.
Mhm.
Any further questions?
Maybe I would have a question. Thanks a lot for the very interesting talk, first of all. So my question is regarding what the uncertainty or the model spread sort of means when you apply a generative model to ensemble forecasts. So let's say you do sort of a numerical ensemble simulation, and then you apply a generative sort of foundation model that has learned the climatology of some observations. And if you apply that to the ensemble, so the ensemble spread will probably change somehow, right? Maybe get nudged towards climatology. And I was wondering whether you thought of what that change in spread means.
Okay. Yeah,
Something
I
like
think
this. Yes.
I really want to share with you about these findings, but maybe next time in the group meeting, and I can talk about it now. So let's see, when we are doing forecast, we are starting from a very constrained place here, right? And we apply our model to propagate a state gas here, a sample here, to the next time step. And if we have, let's say we have 2 members here, and we go to this step, and then from this step, we may have a first guess from our model, right? And if we also have a climatology estimation, we can from this first guess plus some climatology prowl. Let's imagine that there is a data manifold. And then when in your prediction, you cannot exactly fall into this manifold because your model is not perfect. But this data manifold provided by this diffusion prowl will try to drag your imperfect prediction to this data manifold. And if once it falls into this data manifold, it can create an ensemble gas, an ensemble member. Maybe 1 turns into 2. Originally, it has 2 members, and then you propagate to the future, and then you drag into the ensemble manifold, and 2 becomes 4 for the first step. And then for this 4, you go to next time step, and you drag into the manifold, that 4 becomes 8. So we have a tree growing of the ensemble members. So that's the ideal we are trying to realize. Actually, we have realized that, and it looks amazing.
That sounds really interesting. Yeah. Thanks. Looking forward to hear some more in the future.
Any further questions? I might have one, Baoxiang. Relatively towards the end of your talk, you showed this, what I really liked, the comparison to CAN-ESM for the ensemble forecasting. And if you go to the slide where you show the dependence of the forecast error, yes, exactly. So you're essentially creating an emulator of CAN-ESM, and then you show that it even works in a sense out of distribution. That's the green bits, right? So you're predicting real world, although it's only trained on the CAN-ESM world, so to speak. What I find quite remarkable, and I was wondering whether you have an idea, in most cases, it seems that even for the first 8 ensemble, like the ensemble size up to 8, you see the increase of the CAN-CM4 skill. But compared to your emulator of it, the skill increases more strongly. The slope is steeper.
Which one?
So let me see if I can annotate. It's a bit of a, so yeah. So for example, here, that's the sort of improvement of CAN-CM4.
Yeah.
And your improvement seems to be, so you even on the sort of on the set of ensemble, of the number of ensembles that is comparable with CAN-CM4, still your skill increase is stronger.
Yeah, we didn't dig deeper into it, and I think it's probably we need to do more experiments here. I think it's pretty interesting. That is, um, yeah,
So this
I
is
don't know.
exclusively trained on Kenny's M data, right?
No, it's trained on whole sets of data, but you have another condition that is which model is trying to mimic.
I see. Okay.
Yeah, and
Okay.
we are because by that time I was working at this lab,
Mhm.
this Lawrence Livermore lab, and everybody there is talking about these three kinds of uncertainty because they try to disentangle these three kinds of uncertainty. And I know that in seasonal forecast, there is a process bias about different models representing this. And there
Right.
is variability there. And we do not care about forcing, but now we do, because if you look at temperature, it's having really amazing skill because of global warming. It's
Yeah.
not because it has really good skill. And
Yeah.
then say that, can we make representation of these three kinds of uncertainty in a unified machine learning framework, and that's it. And we are using variational autoencoder because by that time we do not have diffusion model. It's 2019, and now we're trying to update it there. And I cannot answer this question right now because I don't know if this is due to some statistical error or approximation error. Maybe the model is not so well trained. But Qitong, if you are here, your duty is to answer this question. That is to investigate how the ensemble size influence the performance of these models. And as VE can already like match the performance of this dynamical model, I hope diffusion can do much better compared to here, especially for like Ethiopia or like parts here. I don't know. I don't know. This model is not so well trained. To train
Yeah.
a VAE is easier, but train
Yeah.
a conditional VAE is pretty difficult. They do
Yeah.
not have something like guidance. We cannot easily guide the contribution from the conditioning information or from the random noise. Something called beta VAE can help, but too tricky.
Yeah.
Mhm.
Okay. Thank you. Next question is by Huang Yu.
Yeah. Uh, yeah, Baoxiang, thanks to your talk. But I'm interested in the ensemble spread generated by the diffusion model. Maybe we can control the condition strength that
Yeah.
added into the diffusion model or foundation model. Then we can control the weights or the weights of the ensemble spread.
Yeah, we have
Right?
already done that. We are controlling.
Yeah.
Yeah.
Yeah,
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 if you
but
Mhm.
but my question is, although we can control the different condition strengths and the ensemble spread wise, but how to ensure or how to confirm it's reasonable in physics?
Yeah, it's very important question. And let's say that how can we ensure it's working very well in forecasting? Here we are selecting the value of W, that is the guidance strength, empirically using a validation set. So in some left out data set, we randomly select different omega values like 1, 2, 3, 4, 5, and we test which one give us the best CRPS, some proper scoring score, how well we make a number forecast. And will this number change with the input? How can we better control this number? There is some paper. Let me see if I can drag it here. Like giving each pixel its strength. Oh, I think there are a lot remains to be explored here. That is how to how to adjust the omega here. And the other thing is that should we stick to this conditional training paradigm? I don't like it anymore. I think we should do like more toward the generative part, and maybe we should get more control on the inverse modeling part. That maybe like more like here, pseudo-guided inverse problem, or like variational perspective on solving inverse problems. And I think those are the directions. And so I think a lot needs to be explored. And those are some technical issues which might not be some selling point in publishing papers. But I still believe that's important. And the other thing is about physical constraints. You're asking that if we can have some physical guidance about how we pick up the W.
Yeah.
I get no idea for now. And I think a very important drawback of diffusion models for now is that their iterative generation nature blurs the connection between the latent and the result. You don't know how to connect the prow to the how to connect the latent to the output unless you use consistency model. Like one step, if you have one step connection between them, and then you can have better inverse modeling. You can have better like reference using inference using this learned model. How to apply physics here? I don't think it fits for this problem. But probably if you go to like modeling of the hydro materials and modeling of the whole state of the circulation pattern, you can add physics constraints there.
All right, maybe a final question if there is one. Otherwise, I think we should soon close this. If there's any final urgent question, then of course we can still go ahead. But if that doesn't seem to be the case, then let us thank Baoxiang again. Thank you so much. This was really, really interesting. And also thank you for the thorough answering of the questions. And so to everyone, our next iteration will be on May 6th. I look forward, the talk will be given by Megan Carney. So more in the applied math climate realm. And we look forward to seeing you there. Have a lovely week, everyone.
Thank you.
Best. Thanks. Bye-bye.
Bye.
Bye-bye.